Hey everybody, Jonathan here. In this video, I'll be giving you my take on section 7.4, which is about partial fraction decomposition. Now, partial fraction decomposition is a technique to convert a fraction into a sum of simpler fractions. And you can always do that to the point where you can just integrate the simpler fractions. Now, the book never gives a general procedure, so that's pretty much all I'm doing with this file. So if p of x and q of x are polynomials, so just a sum of integer powers of x's with all the powers not negative with coefficients, and you want to find the integral of p of x over q of x, so first off, partial fraction decomposition only works when the degree of the top polynomial is less than the degree of the bottom. If that doesn't happen, you can always use polynomial long division. Using polynomial long division, you can express any polynomial in the form of another polynomial plus a remainder polynomial over the q of x, where t of x is just a polynomial, so you can integrate that using the power rule, and now r of x does have a degree less than the bottom. Now, there's a rather complicated procedure in this section with lots of different cases. But what you do in all the cases is that you abstractly decompose your fraction p of x over q of x as a sum of simple fractions, where the denominators of all the simple fractions, they come from the factors of q of x, and they all are either degree 1 polynomials or they're degree 2 irreducible polynomials, which means they don't have any real roots. This means, since you're doing it abstractly, you have to introduce new variables. You now take your abstract decomposition and recombine it into one big fraction. When you can recombine it into one big fraction, you can now set it equal to p of x over q of x. And now the numerators have to equal, and the coefficients of all the powers of x have to equal, and that's going to give you a system of linear equations in your new variables. Then you solve the linear system, and then by solving the linear system, you've now found the not abstract decomposition, you found the actual decomposition, and you can integrate all the terms in that decomposition. And now for your convenience, I've listed integrals of what all the terms in your decomposition might look like. Every term in your decomposition is either going to be one of these forms. To be perfectly honest, you might have to complete the square or something to get it to some of these forms, but in principle, you know how to do that, right? And there just might be other constants throwing around. So with that in mind, it's useful to note that the integral of 1 over ax plus b dx is 1 over a times the natural log of the absolute value of ax plus b plus c. And whenever n is greater than or equal to 2, the integral of 1 over ax plus b to the n dx is equal to 1 over a times 1 minus n times ax plus b to the 1 minus n plus c. To get that, all you do is a substitution. If you let u equal ax plus b, you're just basically integrating 1 over u to the n, and this 1 over a pops out. If you have to integrate 1 over x squared plus a squared dx, that's equal to 1 over a arctangent of x over a plus c. This can be verified just by differentiating this, for example, or you could do it with a trig sub. And then finally, if you have to integrate x over x squared plus a squared, that's going to be 1/2 times natural log of x squared plus a squared. Normally, I would need the absolute value signs, but x squared plus a squared is always positive. Now, just for completeness, I am giving you formulas on how to integrate some of the other factors which might occur in a decomposition when you use partial fraction decomposition. However, any integral where you would have such factors appearing would be far too difficult to do by hand, and you'd use a computer algebra system. But nonetheless, in case you ever get stranded on a desert island and space aliens arrive and they force you to do one of these hard integrals, you'll know how. So what we do if you have the integral of x over the quantity of x squared plus a squared to the n, and here n's bigger than or equal to 2. That's just going to be 1 over 2 times 1 minus n times x squared plus a squared to the 1 minus n plus c. Here you let u be x squared plus a squared, and the x gets slurped into du, and you wind up with a constant times 1 over u to the n. And if you wind up with the integral of 1 over x squared plus a squared n dx, you can use the trig substitution where x is a tangent theta, in which case this x squared plus a squared will be secant squared theta, and when you move that 1 over secant squared theta to the n, which is 1 over secant to the 2n theta, is going to become cosine to the 2n theta. and then you're going to wind up having to integrate cosine to the 2n minus 2 theta. This is a typo here. It should be cosine to the 2n minus theta, which is going to be really freaking hard, but it is in principle doable by the right combination of reduction formulas and the other techniques you learn in section 7.2. Now, normally I don't like to retread what the book does. However, I just want to show you how the steps I outline are applied in this example. So the first thing to do is check that the degree of the bottom is less than the degree of the top. And sure enough, the degree of the top here is 2 and the degree of the bottom is 3, which means we don't have to bother with doing the polynomial long division. Next, we need to decompose p of x over q of x abstractly as a sum of simple fractions. So in this case, this happens by looking at the factorization of the bottom, which in this case is x times 2x minus 1 times x plus 2. And what that means is you're going to have a something over x plus a something else over 2x minus 1 plus a something else over x plus 2. Notice the factors are what go into the bottom of these fractions. This is an abstract decomposition because we don't know what the a and the b and the c are. Now you have to recombine all this stuff. That was my step 3. So right here, you recombine the decomposition and simplify. So we recombine all of this stuff here into one fraction. And then ignoring the denominators, this stuff recombines. The idea here is to combine it into one fraction. You're going to have the common denominator be x times 2x minus 1 times x plus 2. A already has an x, it needs a 2x minus 1 times an x plus 2, so you wind up multiplying a times a 2x minus 1 times x plus 2. B already has a 2x minus 1, so it just needs an x and an x plus 2, so you wind up with bx times x plus 2. C already has an x plus 2, so it needs to be multiplied by x times 2x minus 1. The idea is now when you put this all over the common denominator, you'll all these extra parts cancel, leaving out the original. And now you set the top equal to the top, so we wind up with this equation here. By multiplying it out and looking at coefficients, we wind up with x squared plus 2x minus 1 equaling 2a plus b plus 2c times x squared plus 3a plus 2b minus cx equals minus 2a. And at this point, what you do is you compare the coefficients of the different powers of x. The constant term here is minus 1, and the constant term here is minus 2a, and that means minus 1 is set equal to minus 2a. Whoops. Here, the constant term, the coefficient of x here is 2, and the coefficient of x here is 3a plus 2b minus 2, so you wind up setting 2 equal to 3a plus 2b minus c. The coefficient of x squared is 1 here, and is 2a plus b plus 2c here, so you wind up setting 1 equal to 2a plus b plus 2c. And they write that as a system of linear equations over here. Now, any system of linear equations can be solved, not necessarily efficiently, but you can solve it by taking one of the equations, solving it for one variable, and plugging it into the other equations. So this is nice. You all get automatically a is 1/2. And then once you've got a is 1/2, you can then take this first equation and solve it for b, and then plug the result into the second equation. The b and the a will be gone at this point. You'll only have an equation in c, and you can then solve for c. And then once you know what c is, you can figure out what b is. However, it is tedious, and it is all part of the process, and I will be helping you with this in class. So, going through this process, which the author doesn't bother showing you, which is kind of annoying, you eventually get that a is 1/2, b is 1/5, and c equals minus 1/10. So remembering that a was what was the coefficient of 1/x, we get the explicit part of the decomposition 1/2 times 1/x. b was the coefficient of what was of 1/2x minus 1. So since b is 1/5, the explicit decomposition has 1/5 times 1/2x minus 1. c was the coefficient of the x plus 1/x plus 2. So we wind up with, and since c is minus 1/10, we wind up with minus 1/10 times 1/x plus 2 as part of the explicit decomposition. Now, using the rules that I showed you, in fact, for this, we only need that first rule. where the integral of 1 over ax plus b dx is 1 over a times natural log of the absolute value of ax plus b plus c, we immediately get that the answer is 1/2 natural log absolute value of x plus 1 over 10 natural log absolute value of 2x minus 1, because you wound up dividing by this 2. That's where the 10 comes from, minus 1 over 10 times natural log absolute value of x plus 2 plus some constant.